Welcome to Advanced Data Analysis 2 with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, we'll be completing Chapter 9 on models with factors and predictors. And we're looking at the faculty salary data example. We've just finished in the previous video a three-way factor model, a three-way ANOVA model. And we're going to look at two other analyses in this video. First, we'll start with an example with only the continuous predictor variables, and then we'll put everything together. So that last analysis is really the one we're working up to. So we have year and year since degree that we can use to predict salary. And I'm going to start off just by creating two plots. And these plots have lots of data in them. So if you think about how many dimensions are represented in the plot on the left, we have salary on the vertical axis, we have year on the horizontal axis, then we have three factor variables. We have the size, other and doctorate, small and medium. Then we have got three colors for full, associate, and assistant professors. And then we have shape, males and females. So there's all the data basically in the data set is being plotted here. It's a little bit hard maybe to make sense of this. Let's start by thinking about this. We have assistant professors that are blue. And so the year, recall, is the year at the current faculty rank. So you'll start at 0 and you'll be that professor for a certain length of time. And most assistant professors in their 6th year, at the end of their 6th year, will be promoted to associate professor. And so we go from blue up to green. You get a big salary boost, maybe not quite that big in my experience, of 50% of your salary. But then you start over again at 0 for associate professor, and you associate for some length of time, and then from green you'll become red, and then you'll be full until you retire. Some people for a very long time. YD is the other continuous variable, and that's the year since your last degree. So whether you stopped with a master's degree or whether you stopped with a doctorate degree, when you got that degree, that was 0. And so here, this is basically the same data as on the left, but you can see the shift, right? Here, if you're an assistant professor, you start blue, and then when you get promoted to associate professor, you just go up vertically. And then you're green for a while, and then you go up vertically to red, and then you're red. Okay? So you can see really the major stratification here is by faculty rank in terms of salary. Okay, but we're going to ignore all these other factor variables for now and just look at the continuous variables. All right, so here I'm looking at a linear model that uses year since your year in your current faculty rank and year since degree, and with the asterisk we also get the two-way interaction. And if we look at the summary for this, we see that there isn't a suggestion of interaction, but that the two main effects seem significant. So we'll look at the main effect model with just those effects, and in fact, they both remain significant. So it's not only how long you've been, your salary doesn't only depend on how long it's been since you got your degree, but also the number of years that you've been in your current rank. But notice rank isn't in this model, so this is sort of a strange model. It seems that we should have that in the model. You can see this R squared is pretty low. It's 57, almost 58%. If we page up just for comparison to the ANOVA model from the previous example, excuse me for jumping around for a second, the model with only rank, okay, the model where we just predict salary with rank, explains 75% variability. So rank as you can see in the plots too, is by far the largest predictor of salary. You get these big jumps. Though certainly there's sort of this linear increase with year since your last degree, but that increase is also pretty much correlated with what faculty rank you are. All right, so that brings us to the main model that we're going to use to look at this data. We're going to put everything in, but we're going to make some decisions first. So all right, let's see. The plots we looked at helped us understand this data, in particular the plot of the salary against the ranks, years in rank. Using rank as a plotting symbol suggests that combination predictors and factors will certainly be better. There's no evidence of non-linearity in the plots so far for those continuous variables. And so I won't consider transforming the years since degree or the years in rank or the salary. Note that there is increasing variability in the salaries for increasing years in rank. Okay, so that's sort of a natural condition, I think, of when you're an assistant professor, right? A lot of assistant professors start sort of at the similar salary, but your salaries will deviate the longer you're a professor. So this is a monster model. We're going to include of the full model. This is going to have the 5 main effects plus all the pairwise two-factor interactions, or two variable interactions. So we have sex, degree, rank, year, and YD, the year since your degree. Then we've got the 10 interactions. Okay, those right there. So, okay. All right, so we're going to start there with our model. Here is one way to specify this in their syntax. We're going to have a linear model with salary, sex, rank, degree, year, and year since degree, in parentheses, and squared. That's going to give us, the syntax for that gives us all the main effects and all the two-way interactions. So let's look at the ANOVA table for that. And this is probably one of the larger models that we've seen. We have several 2-degree of freedom tests. That's when we've got associated with rank, because we have 3 ranks, so we have 2 degrees of freedom for those tests. And boy, when you got everything in there, look at the p-values. They're all pretty big. And that's because there's a lot of collinearity between these variables. Basically, there's lots of variables here that are explaining variance that are also explained by other variables. So none of them seem to be important after controlling for all the others. Not a big deal, but that's a good place to be starting. This time I'm going to use BIC, the Bayesian Information Criterion, and this will push us towards a little bit more of a parsimonious model, a slightly smaller model. And we specify this, recall, by letting K, our penalty term in the information criterion, be equal to the natural log of the number of observations. And it occurs to me right now that this should actually be slightly adjusted. N row, this should be N row minus 1, because we have 1 observation, I think, with, oh no, that was a previous data set. This is fine. Okay, very good. Typically, I think we want to do this with NA omit to make sure we're only looking at observations that have the full data. All right, so we're just going to start off, and I'm just going to sort of start scrolling down pretty quickly. We can drop sex rank is the first one to go, and I'm going to just scroll. Scroll. Okay, we're dropping tons of interactions. We're dropping some main effects. In fact, right here is the moment when we drop sex. I was looking to see if it said which step number it is, but we're not. So we're dropping sex right there. Degree, And when we get down to the bottom, we have rank and year in this model. All right, so our final model from backward selection is salary predicted from rank and year in that rank. Now we can use, because we've done now backward selection, we can see whether at the end now, whether we can add in, using the add1 function, whether we can add in any of the variables that we may have dropped early on. And another strategy we could have used, if I page back up for a moment, we did do direction backward. I think there's a direction equals step or stepwise, or both, one of those. They're all synonymous for doing backward and forward selection one step at a time. And that may have been a slightly better choice here. But here we are, we're at the final reduced model. We're going to start at that reduced model and see whether we can add one variable back. And we're considering the full set of variables from this model specification to see if we can add anything back. And our result from there is that the best AIC value, or in this case BIC, is when we just stay with the model that we have. The next best variable to add would have been sex, but there isn't enough evidence to say that we should include it. It would have a p-value of 0.5. All right, so let's look carefully at our resulting model. We'll assign that reduced model to a final model and take a look at that final model. Both rank and year are significant. Looks like when those promotions are the times when you get those big jumps in salary, okay, going from assistant to associate and then up to full, it basically jumps of $4,000 or $5,000. But for every year within a rank, you only get about 300. So makes sense in this case to get promoted. Okay, we're explaining about 84% of the variability. From our first model, we had rank before, and now we've added year. So we get 10% more in our R-squared. We can use, because we don't have any interactions, we can use LS means. Actually, we could do it even if we had interactions, to see what the difference is between the ranks, okay, as we did it before. And these are pretty similar as they were in the initial analysis. So let's discuss some of these results. The selected model is fairly simple. We have one factor variable, rank, and we have one continuous variable, year. It explains a high proportion of variability, and we started with a full model of 20 variables, right? And it had an R-squared of 0.89 if you scroll way up to the very beginning. When we get down to the bottom, that only has 3 degrees of freedom, only rank, which has 2 degrees of freedom, and year, which is 1 additional degree of freedom for a total of 3, we only get down to 0.84. So we lost 5% of predictive ability, but we simplified our model from 20 to 3 degrees of freedom. So that's a very worthwhile simplification in my opinion. So if we look at the parameter estimate table, we can plug in and get separate equations for each rank. So here's our intercept, and then here's our slope term for age. And full professor was our baseline group. Associate professor subtracted 5,000 from the full, and so here's what you would predict for salary for an associate professor, and similarly we subtract 9,000 for assistant professors. So there's our 3 regression lines. We've got parallel lines with the same slope of 375 and with different intercepts. All right. So you might be tempted to conclude So now things are going to start to get seriously, okay? In terms of bringing a greater context to the analysis, the context that doesn't live in the data itself. You might be tempted to conclude that rank in years in rank are the only effects that are predicted of salaries, and that differences in salaries by sex are insignificant once these effects of rank and years in rank have been taken into account. However, you must be careful because you have not done a diagnostic analysis. Okay, so we haven't looked at the diagnostics for this data yet. The following two issues are also important. Okay, I'm going to skip over the diagnostic simply because there's other things to be considered, but this is always important. All right. A sex effect may exist even though there is insufficient evidence to support it based on these data. Okay? Lack of power corrupts, and absolute lack of power corrupts absolutely. If we are interested in the possibility of a sex effect, I think that we would be better by focusing on how large the effect might be and whether it is important. So a simple way to check this is by constructing a confidence interval for the sex effect, and then see whether there are, look at the confidence interval and see whether there's big values that are plausible based on the confidence interval, and that would suggest sort of how important that sex effect possibly could be. So let's start with the simple additive model that we have and include sex with those other variables. All right. I'm choosing this model because omitted effects are hopefully small, and because regression coefficient for sex indicator is easy to interpret in the additive model. All right, so let's use the update function to take our previous final model and add sex to that model. So now we have final.sex, and here is the model that includes sex. You can see that it's not significant, but we have an estimate of 500 and a standard error of 800. It's a pretty large standard error. All right, so men are the baseline group for the sex effects. So the predictive salaries for men are $524 less than for women. Yes, that's correct. This is a positive value for female. So females actually here are predicted to earn more than males. Okay, after adjusting for rank and year. A rough 95% confidence interval for the sex differential is the estimated sex coefficient, okay, so 524, plus or minus 2 standard errors roughly, okay, so 835. So here's our confidence interval. So the range of plausible value for the sex effect would appear to contain values of practical importance. If there's a difference in salaries between males and females of $1,000, or $2,000, those are possibly big enough values to be concerned about. Maybe, in my opinion, an even more important concern was raised by Mr. Finkelstein, or Finkelstein, depending on where in the world you learn to pronounce vowels, in a discussion in the Columbia Law Review on use of regression for discrimination cases. So, a variable may reflect a position or status bestowed by the employer, in which case, if there is discrimination in the award of a position or status, that variable may be tainted. In other words, if women are unfairly held back from promotion through the faculty ranks, right, so that there's discrimination and males are preferentially promoted and women are not, or there's other competing factors that maybe hold women back, in terms of like math in elementary school, or there's all sorts of pressures, right, that are different for men and women. Women are encouraged to read at a young age where Boys typically aren't given quite as much encouragement in that direction. There's all these social pressures and biases that change the experience, and therefore what people are good at and how people treat each other. And all those things exist from when you're born all the way up to when you're getting promoted. Okay? And so all of that social stuff is happening. Therefore, using faculty rank to adjust salaries before comparing sexes may not be acceptable. Okay? Because it's not just about what your faculty rank is, but how were you able to get promoted? And was it as easy for one person as for another person who has different characteristics not associated with their job performance? Okay. This suggests that analysis comparing sexes but ignoring rank effects might be justifiable. Okay, so let's see what happens if you ignore rank but include sex instead. So let's just sort of do something simple here. There's maybe a more complete analysis where you'd ignore rank earlier on in the analysis and you do the full backward selection again. But let's just put sex in there instead and just quickly see. If you do that, sex is not significant at a 0.05 level, but there's what psychologists would call a trend, a value between 0.1 and 0.05, something that looks like it could be significant if only you had different data. But here I would just say it's this is not significant at a 0.05 level. But the estimate here, notice once you remove rank and you're looking at the year since your degree, the difference between men and women is about $2,500. Okay, we haven't done model diagnostics. I'm just interpreting what the model suggests right now. But for every year that you work, you earn an additional $380, and that females on average earn about $2,600 less than males. That's what this says. This explains not as much variability as a model only with rank, okay, which was like 75%. So this is maybe not a great model. But we haven't looked at any diagnostic plots, so I'm just bringing up different considerations in model fitting. All right, similar as before, we have insufficient evidence that sex, at least at a 0.05 level, that there's a difference between sexes here. And it's basically because we have lots of variability in salary. Okay. Furthermore, if we included an interaction, that interaction is insignificant. So I haven't shown that here. So rank and sex, however, might be confounded, right, for the reasons I described earlier about how people get promoted and that there may be systematic differences. Now, this data doesn't have any evidence, and I don't have any personal evidence of that. In fact, in my department, mathematics and statistics at UNM, there's more females than males, and in fact, one of the largest grant getters in the department has consistently been a female. So, it's not working. There isn't a systematic difference that I observe in my experience, but there certainly is in the world. So I guess I'll leave my comments there, and that's the end of chapter 9.